Okay, hello everyone, and welcome to my talk about Kubernetes API performance. I'm Marek Siarkowicz. I'm the SIG lead of etcd, and I contribute to also API machinery. Unfortunately, Madhav was not able to join us today, so I will be, hope I'm enough to talk about the performance of API. So the plan for today is explain what is the minefield in the title. We will try to understand on example why you can easily get hurt if you don't understand the API performance. We'll try to propose a couple of ideas how we can navigate, and hopefully maybe we could diffuse it. At the end, I have a couple of results from performance metrics, so we could see how it turns out. So overall, Kubernetes is awesome. Like, you can take your containers, you can ship it. It works really well. Like, we have pretty big conference. I think it's testament to that. But not always it can turn out how you can think. Some things are harder, sometimes there are incidents, but I think, in my experience, there are some areas that you're just destined to fail, unfortunately, that are not well documented, that are still a tribal knowledge that is spent between maintainers, and if you don't ask them, you might get hurt. So for last year, I've been looking into the API server performance, and hopefully we can diffuse some of the problems today. So the problem that I want to talk about to you is the problematic usage or abusive usage of CRDs and operators. So in one of the incidents that I was working on GKE, we had a pretty small cluster. It seemed pretty small relatively to the things that we run, but still, customer upgraded as operator, and everything worked for 2 weeks. And just when everyone already thought that we are done, the memory spiked 20 times. So what happened? Like, why did it spike every like couple of days and totally took down the control plane? And how a like 15-node cluster can go down? Well, Kubernetes apparently supports 5,000 nodes. So since 1.6, Kubernetes runs a weekly test that has 5,000 nodes, 15,000 pods, or 150,000 pods, 10,000 services, and everything. So it should work, right? The problem is Kubernetes tests its own scalability, focusing its own main pipelines and its own concerns. So when you go into CRDs, you might find that the project that you have picked from the shelf never tested anything beyond like 10 nodes. And a lot have happened since 1.6. So now everything is a CRD, and yeah, anyone can create a new, which means there can be a lot of things that are lower quality. One of the maybe unique patterns about Kubernetes that people forget is that compared to traditional application like SQL, in Kubernetes, you're not interested in a single user or some data related to this user. In Kubernetes, we still have a database like etcd, but reality is the consumers of API are controllers, and controllers, what they do is they reconcile. So to reconcile, they need to find old state, understand it, make a decision, and transfer to the new state. But they are really processing everything that happens in cluster. So it's not one-to-one, one user comes or one client comes and makes one request and they fetch one row of data. You have one controller that comes and fetches 150,000 pods. How do you handle it? What Kubernetes did? So I could say, or personally, Kubernetes was originally not really designed for large data, or at least for the CRDs that we have today. Going back to the incident, it turned out that customer had 100 or 500 megabytes of data in one of their resources. How do you handle that you have a controller or a client that every couple of seconds fetches 500 megabytes of data? And each of those requests was allocating gigabytes and gigabytes. So even though Kubernetes has limits, has quotas, each object can be 1 megabyte or over 1 megabyte in size, and there is you can easily get the size of a resource or size of all the pods or CRDs or your config maps to gigabytes in size. And really, Kubernetes overload protection doesn't work here. APF, so API priority and fairness, mostly accounts for the CPU usage and doesn't account for memory. So those 400 gigabytes of data that was allocated was just coming from a couple of controllers that were consistently listing a lot of data. And they were getting them, but with the cost of API server umming. So let's deep dive how those 400 gigabytes came out. So first, when you make a list from the client, Kubernetes client, the request goes through API server or is directly fetched from the etcd. API server just transfers the request from a list to a range, which is just similar but a little bit different semantically. etcd then fetches the data, reads it from the disk, and deserializes it, so it can prepare the response. Next, you need to serialize the response into proto, because etcd uses gRPC, so it needs to write the protobuf serialization. It sends this data into the API server that then receives like in this example, half a gigabyte of data and loads it also to memory. So now we have 3 allocations. If you want to use the data, you cannot use just bytes or a blob of bytes. You need to decode it. So API server needs to decode the data, and again, which requires copying it copying the memory. Sometimes, depending on your request, API server in the storage layer can do some filtering, so that, for example, when a node or a kubelet fetches pods on its node, will not return them, it will not get back all the pods in the cluster, it will just get a subset of them. But still, in most cases for controllers, filtering doesn't really filter, it's just a pass-through. And at the end, for client to receive the response, API server needs to encode the data back again. So if we count, we have 5 allocations. That's a lot. If you want to fetch a gigabyte, you will get 5 gigabytes. An API, if you have multiple clients like this and they're misbehaving, unfortunately, Kubernetes will not protect you, and those 500 gigabytes were just 10 clients or 20 clients that were fetching this memory and pushing API server to allocate and allocate. To mitigate this, Kubernetes uses something called caching. It uses caching. If you want, there was a previous talk by Madhav about exact details about how cache works. But let's look at it again quickly. So cache is a component in API server that has its own storage, which stores the subset of state from etcd. And this cache is filled by API server just requesting all the data from etcd, decoding it once and storing in memory. So cache has already prepared a response for a request that is ready to be, or it's already decoded and it's ready to be used. If because we cannot do it for each request and the data changes, cache also maintains an open watch to etcd that will send updates on each change. So instead of, if we have half a gigabyte of data, still updates might be just 1 megabyte because one pod change or one change in the object will send only one event which will have just 1 megabyte. So we are now just decoding 1 megabyte at the time, which is much better than before. So if there is a request from the client, we will just go to the cache, and from the storage, API server will just need to encode the data, so resulting in just 1 allocations. Isn't it great? Like, caching is great. We got back from 5 to just 1 allocation. Is it enough? Unfortunately, no. If you look at the full table from all possible arguments in API server, only 2 cases use really cache, and 2 cases use cache but without ignore a limit. So if you cannot limit the data, you can just get gigabytes of response. So that's a lot of reds, making it very hard for most users to know what kind of performance they're getting, because they don't know if they're hitting cache or not. And the top line is the default configuration. If you request by default empty request without any parameters to Kubernetes, it will be delegated to etcd. And so this is a state of Kubernetes 1.30. Let's see if we can improve it. So, so how we can, if the situation is so bad, is there any way that we could navigate it? So if there is a full minefield of wrong decisions that we can, wrong parameters that we can pick, how we can know what path to take between the mines. So first step would be reading the manual. I assume this is KubeCon conference. Everyone here read documentation, Kubernetes documentation. Everyone read your cloud provider documentation, because it basically says you should not do what I shown before. You should not have huge resources. You should limit your sizes. And this is consistent with the recommendation of 6, scalability, of using list watch pattern. This is consistent with scalability, trying to set resource version, using protobuf to reduce allocations. GKE also recommends limiting the storage, and I would say, like, you should really watch out for the sizes of the objects to make APF work better. Second option would be to run your own scalability tests. Like, if you cannot read or know where the mines are, can you have a tool to find it? And the answer is yes, you can run your own scalability test to verify before you go to production, before you upgrade anything, that there was no huge regression. And until you really run a similar environment, and until you validate the exact dimensions that you run in production, you don't really know. There could be just a small bug or small change in a one-line change in the PR or between versions, or one small change between versions of operator that you run that could totally go from using a cache to sending requests to etcd, resulting in huge amount of allocations. So I think we should encourage all the projects in open source to set their own scalability goals and ask for budget from CNCF to do the testing. Like, if we care about our production, why we should run scale test everything our own? It's an open source project. We should agree as a community to set a common goal that will be maintained throughout all the releases. So if the 2 first options failed, can we defuse? Can we defuse and remove all the mines? Can we live with can we improve the situation and make it available to everyone, so everyone can understand the scalability and not need to read a book about this? But before we go into fixing Kubernetes, first we need to take a look what is a resource version. So a resource version works as a logical clock, a global int64 that every time anything happens to etcd or Kubernetes, any write, any update, this number will be increased so that we know we have a single global order of everything that happens in the system. This brings us to the semantic of the list. So when you have a operator or a controller or a user asking about a list, they really ask about some particular meaning or some particular snapshot of the time. So Kubernetes and etcd support not only getting the newest data from latest state, but it allows they allow you to pick historical values, so snapshots of the state from before. You can ask Kubernetes about any state of the world that it was aware. So basically, ask, hey, give me any response from any time that you have. You could restrict the staleness of the data by asking that the response will be not older than some particular last time. So, for example, from last what you've seen. You could also ask about the most recent. So normally for most databases, you usually ask for the default. What is the state of the newest state that is available? And this is the default when you send a request in Kubernetes. And you can ask about historical, about state of Kubernetes from some exact resource version, which would be asking Kubernetes to go back in time and check what was a state of Kubernetes, I know, from a couple of minutes ago. There is also a continuation, which is a mechanism that you need to support pagination. You need to be able, it's basically extension of the exact semantic that you allow not only ask about some older snapshot, but also with some shift, so you don't need to read the same keys. So you want to continue the list, but from you want to continue list from some old snapshot, but you don't want to see the same keys at the beginning. So you could say it's a time traveling machine. So let's look how those semantics work on the caching. So if you ask about any resource version, you will get just any data that is currently available in the cache. Assuming the cache is initiated and ready to serve data, etcd could be far beyond forward. Maybe the watch hasn't yet been updated, so the cache can be stale, but you will ask, you will get a response from the cache. That's easy and cheap way. You can ask about the not older than, and it will just make Kubernetes wait until the resource version is in the cache is fresh enough. And when it is, it will respond. But here the requirement that there needs to be other client that will update the resource for you. So first there needs to be a client that will send an update and will increase the revision in etcd that will cause a new event to go to the cache and update the resource version here to 120, which is more than one requested revision or resource version, sorry, 100. And that will allow the wait to stop, and you will get back the response. So we have two things that we can easily serve from the cache. What about the last three? So those are the newest improvements in Kubernetes since 1.30. So let's look how we can, how those problems were solved. To get most recent, let's look how etcd does it. So if you disable cache in Kubernetes, the most recent request will be just served from etcd, and etcd will serve you what is the latest state in it. So cache could be stale, but etcd will always know what is the latest state of it. So this goes to back to the definitions or to the previous slide of API server working just as a pass-through. But on cache side, how do we know what is the freshest data in etcd? Like we have some resource version in etcd. How we know this is the newest resource version in the whole cluster? So to do that, we need to first, maybe we could ask etcd, like let's ask etcd what is its newest version. So we can make a simple very cheap request to etcd and ask it to give us the resource version. And then we know that we need to wait for, if it responds with resource version 100, we know that we need to wait until revision hits 100. And second, to not need to wait for any other things in the system, so any other update, we also need to do some fixes in the watch. So when we know we are waiting for resource version 100 and current cache is not up to date enough, we can go to watch and maybe poke it to ask for progress. So etcd for long time, I think like since 3.3, supports watch progress notification. So the client, here API server, can request an update on etcd. If you are aware of the bookmarking mechanism in Kubernetes, it's the same principle just on Kubernetes side. So if maybe there is no update in etcd, but still if we requested a progress, etcd is happy to give us the confirmation that yes, you are up to date. Maybe there was no event and no, maybe not any data didn't change, but still it can inform the cache that it's up to date with the resource version. And this allows us to fulfill the check of minimal required resource version and get a response to our client. So we are done with the first one, or the third one, and this feature is called consistent reads from cache, and it's implemented in Kubernetes 131 by default. And another case that is much harder is what do we do if a client requests about exact resource version. So here etcd can magically go back in time and understand if user is asking about the old resource version and has still the data to serve the client. So it will be able to send a resource version with equal 42. But on cache side, we don't have this information. We don't store all data. We don't know how cache looked like 5 minutes ago. So can we implement that? To do that, we need snapshots. But before we go to snapshots, we need something that supports snapshotting. So in Kubernetes 1.32, we introduced a new reimplementation of the storage for cache, which is based on B-trees. And B-trees are awesome. So not only it brought 25% performance improvement, reduced allocations by 15%, but also introduced a new superpower. We can snapshot and clone the cache. So not only we get one superhero, we can get at any moment as many as we want. So like I said, we can clone the cache. So if there is a watch event, we no longer need to update the storage and lose the historical point like previous version. We can now get this information and clone the storage before we apply a new change. And we can do it multiple times. So if we get resource version 20, we can save it as a snapshot with resource version 20. If we get another event, we can clone this storage and get and update it with new event that increases the revision to 42. And now we have two snapshots. And we can do it again and again on every. And this allows us to have a full history of everything that happened, all the snapshots of all the states of etcd in memory, ready to decoded from etcd and ready to be served. So if a client requests about resource version 42, we can just simply go to this snapshot. And if we don't have resource version because watch cache could be not initialized or has a cleanup mechanism and we might not be able, we'll still delegate the request to etcd because we don't want to break our users, we want to be consistent with the previous behavior. So this feature is called list from snapshot. and it's now alpha in 133, which means it's still not enabled by default, and we are validating it in our testing, and we are validating. We want maybe you to help us validate it to make sure that it's production ready. But hopefully we can we can bring it to beta and make it default in 134. So this solves for us the case of exact and the continuation. Like I mentioned, continuation just is a additional case for the exact with additional key or shift in a keys that we read. And this works up to 75 seconds because we clean up the watch cache after the events are older than 75 seconds, which is enough for like 90% of cases. So can we celebrate? Almost. If you read JSON code or if you ever tested API server, even serving from cache will require you to do more allocations because JSON was not really also designed to handle large data. So if you request from API server 1 GB, or you will API server memory will increase by around 2. So instead of having just one allocations in the encoder, we'll double that, and that's also not great. So maybe we could fix that. The answer is yes. There is a CAP, streaming collection encoding in 133 that is enabled by default. So it immediately went to beta, and it basically re-implementation of JSON and proto encoding. And this makes it really efficient. Maybe just to give you hope, we do this custom implementation is assumed to be temporary because Golang is working on a better implementation of JSON encoder version 2 that will solve this problem. But we want to bring the benefits to you quicker, so the next Kubernetes release will not require any additional memory for encoding, at least for JSON, and protobuf. So this, instead of taking half a gigabyte of payload and encoding into one huge gigabyte blob, it will just stream objects one by one, making allocations much lower. I promise performance results. This is our official benchmark for all of those efforts. So benchmarking a list has gone down from 70 gigabytes of memory usage to just 3. So to summarize, caching is hard. It took Kubernetes a very long time, and still there is some work to do, but we will get it right, and thanks to that, the memory problems will disappear. Before 131, the default request to Kubernetes needed were served from etcd, making it not very efficient. But thanks to 131 improvements, now even default requests will not require as much memory as before. And streaming in 131 will almost eliminate any memory allocations in Kubernetes and etcd thanks to the streaming list. And hopefully we'll get the list from storage working soon in the next release, and that would make Kubernetes fully safe from memory perspective. So thank you. That's all from me. This is a feedback QR code, and we are open to questions.
Hi. I was just kind of wondering, so like, if we're having these noisy neighbor problems when we're using CRDs inside of the cluster, like, I guess that's sort of the perspective that I have here, where like, you know, the memory usage here is exceeding our expectations and how the API server works. Like, why do we encourage movement towards like CRDs and sort of using Kubernetes as like a low-code solution for creating and managing resources than like externalizing these things. Like when should you and shouldn't you use CRDs, I guess?
I think, or extending Kubernetes is awesome, and a lot of work has been put into that. It's still, I would say, I think the assumption is there were not many projects that use CRD do scale testing, and Kubernetes itself, because it doesn't have default CRD, let's say, example CRD that it will scale test because it doesn't want to opinionate it, then you get into the problem CRDs are not scale tested and we delegate it to the other projects. As for doing it externally, there are options to extend Kubernetes by running a separate API server or your custom re-implementation of API server. It just turned out to be too hard for most users. So it works for some use cases, like metric server, but most users just don't want to manage etcd. They don't want to write their own API server. They just want to inject. So I don't know if we don't encourage it, but it's basically still working. I would say it's still work in progress, and we need to catch up. Performance needs to catch up for the biggest projects that currently exist in the ecosystem.
Thank you.
So about the JSON encoding related performance gains and memory gains, I guess, are you pre-encoding the list response already, or are you just converting the pod list response to a JSON stream response, like, I guess one object per line sort of thing?
So this is not related to object per line, or maybe do you mean watch list effort?
So at the end, I guess memory usage drop, the big drop that you got in the API server, was that related to JSON encoding?
Yeah, yes, that is the results from implementing JSON, custom JSON encoder.
I see. So that JSON encoder basically, is it like just stitching the objects together in a custom encoder, or is it like just not allocating too much memory? I'm trying to figure out why is it.
So before we had one structure, like pod list, let's say, and within this pod list you can have gigabyte of data within the array that has items.
Right.
So instead of doing that, the custom implementation is basically detecting or trying to recognize what kind of object it is. If it's a list object and has these fields, then we will do custom implementation of at least the top level, and it will just go re-implement the JSON as you write token by token, and then when it comes to list, it will write each thing separately. So Kubernetes by its own supports the writer interface, and technically JSON too. But if you look underneath the implementation of JSON, it just takes the whole list structure and encodes it in memory into bytes, and then passes it to the writer. So which means it doesn't do release streaming.
Makes sense. So inside the cache, I guess watch cache, are the pods themselves already stored as encoded JSON, or are they like in just?
No, because of conversions and everything, you store them decoded from etcd, because it could be, you could store data in etcd in Proto, now in Seaboard, which is alternative also encoder. So you don't know what client will request. So watch cache, basically you store decoded objects like in Kubernetes native structures, and then when you encode, you base it on the client headers and request.